calcium carbonate, which is a solid, and I put it together with HCl, which is aqueous. And we would get from that reaction, what type of reaction is this? Double replacement, okay? So we would end up with H2CO3 plus CaCl2, and then we would have to balance it, okay? And in this question, you might be told, oh, this is aqueous, and this is aqueous. But seeing as you are an AP student, you should know that whenever you form carbonic acid, it will break down into, anyone know what it breaks down into? Water and carbon dioxide. What state is water? Liquid. And what state is carbon dioxide? Gas. So what you would do is you would just cross this out, and instead of writing that, you would write H2O plus CO2. I like putting the H2CO3 first because it makes predicting the products and balancing the reaction easy, right? But if you happen to just go straight to the H2O and CO2, that's also totally fine, okay? What properties could we use? Oh, and before that, I guess I should say that this particular is a powdery white solid. Discuss with your partner, with your neighbors. What could we monitor to see what the rate is? We could measure a change in what? What's one method? Yes. Yeah, you would look at a decreasing mass of the system as the gas leaves the system. So you could look at a change in the mass of the system over a change in time. So that's an excellent way to do it. What's another one? Yes? We could measure the gas produced. What quantity would you like to measure about the gas produced? Pressure, sure. You could do a change in pressure over a change in time. Yes? You could do a change in volume over a change in time. Anyone got another one? Yes? Mass of CaCO3. And this is why I brought this one up. If you have something that is powdery, it's easy to measure its mass at the beginning, but it's really hard to measure it partway through the reaction or at the end of the reaction because it's powdery. And you would have to make sure you collected it all, make sure it was all rinsed off, and make sure it all got dried. So although technically you could measure the change in mass of CaCO3, it would be more difficult. We tend to use that more for like if we have a metal, right? Because a metal is like, oh, I've got a chunk of metal, now it's just a smaller chunk of metal. Do you know what I mean? So that's why I brought that one in particular. I would tend not to do a change in the mass of CaCO3 over a change in time because it's hard to measure after being wet. There is one more way we could do. Yes? We could use a pH meter because we have an acid, right? So we could use a pH meter. Change in pH over change in time. Actually, I wouldn't say a change in pH over change in time. I would probably say a change in the hydrogen ion concentration over the change in time, but we would use a pH meter. How are we feeling about these types of questions? Thumbs up, thumbs down, thumbs in the middle. Okay, mostly up, a few in the middle. If you're feeling in the middle, don't forget, we've got Flex today. Yes? Do you have a question? Yes.
Could you do B from page 26?
Page 26B, yes. 26B. Okay, so we have all gases. So if we have all gases, by definition, this has to be a closed system. Okay, because otherwise the gases would just scatter to the winds. Yes? So for this one, I would tend to look at either pressure or volume. That's a very good question. So I would start with, I'm going from less gas to more gas, okay? So I would start with maybe my reaction vessel like this. And then I would have my little stopper. And then I would have like a little hose here. Okay, presumably, and it goes through the stopper. There are stoppers that have a hole in them. Okay, I would presume I would start with this pinched off or something like that. You know, I would like have like a little clip or something to, and then as soon as I put everything in there, I'd put it on there and I'd like open it up so that when we start producing more gas, I would have it attached to a syringe. And then the gas would push on that. I don't think it's an excellent way of doing it. I would tend to use pressure instead. I think pressure is a much more reasonable way to go, right? Because you've got some volume in here. You could also use a eudiometer or a gas collection tube where you have your reaction vessel, you got your stopper, you got your little hose thing. And this would then go into our gas collection tube, which shouldn't be that big, but I can't draw it. So there's our gas collection tube, and this feeds up into there. And this is filled with water. right? And then this is in a container, maybe a big bowl that has water. Right? And then as it produces more gas, we will get bubbles. And that will displace some of the water. And the water level will go down over time. Yeah? Where does the water go? It goes into the bowl. So normally, if you have something like this, actual official pneumatic troughs, which is what they're called, they often have a little valve on the side that you would just say, if you had your thing here, it would just sit over the sink. And so any extra water that gets above that level would just, dump into the sink. Did that answer your question? Okay, cool. Yes. Yeah.
But if you have gas reactions and gas products,
Yeah.
why does it make more gas? Because you're using up the reactant gas to make gas.
You go from one molecule to two molecules.
So it just
Because the amount of space taken up by a gas just depends on the number of particles, not the size of the particles. Because gases, if you remember your ideal gases, an ideal gas, the actual particle itself is considered to have no volume. Right? So the volume of a gas just depends on how many particles there are. If you have twice as many particles, if the pressure is the same, it will take up twice the space. Yeah? Yes? You know what? Honestly, I don't know how you would use a spectrophotometer on this one. I don't think they're going to ask you about that. And certainly I am not. Okay? I think, because it's green, you could be like, sure, spectrophotometer. Maybe there's a gas spectrophotometer, but we certainly do not have access to something like that. Yes?
we talked about this last year, so neon gas and stuff. The electrons jump.
Yeah.
You'll do something like that.
No. When you do that, basically you need to have a vacuum tube with the gas in it, and you put an electric current through it and you zap it. So it does not lend itself well to mixtures of gases and reactions going on. Like the tubes come sealed and they have a single gas in them, and you put them in a machine, and totally different sort of a procedure. Yeah. Yes? If you've got no other choice, that's what I would say. If you've got no other choice, so let's say are there any in here where we have no other choice? No, we could measure the mass of the copper, mass of the silver. We could do spectrophotometry. This one, pressure. You could do mass of the solid. You could do, yeah. I mean, honestly, when I did it, it was like in a biological system. And so there was like there were no particular solids you could look at. You were just looking at one particular product that didn't meet any of these criteria. So basically, I would say, yeah, you're not going to be using titration, Anything else? You have a question, yes, and then you. Conductivity for gases, no, they're not ions. Yeah, you need to have ions on the products or on the reactants, or a difference in the number between both, basically. Different number of ions on either side of the reaction. You had a question. Question 3. Yes. Why would the concentration of copper metal not be an acceptable answer for question 1A? So here's my piece of copper metal. Okay, and concentration is moles per liter, yes? And the density is grams per liter, yeah? Okay. And you can interconvert these, yes? Okay. So if I have a smaller piece of copper, or actually I'm going to do aluminum because I know the density of aluminum, and I won't have to make it up. The density of aluminum is 2.70 grams per, well, it's actually grams per milliliter, but you know, you could convert that to liters. What is the density of aluminum in a smaller piece of aluminum? Same, 2.70 grams per milliliter. So what can we say about the moles per liter for each of these? They would be the same. So solids do not have concentrations because they're kind of irrelevant. The density would be the concentration. And concentration should be something variable. It can really, concentration is only used when you have a solute and a solvent. So in this case, you don't have a solvent, you just have the metal. Does that make sense? Cool, good question. Anything else? Yes?
I'm not too.
Yep.
Understanding that you can't measure the volume of water because it's an increased solution, so you're measuring like one region and one in solution.
Yeah.
But would you not be able to do like mass of the water to find the find the original volume of water and then subtract the
Okay, so first of all, this amount of water is minuscule compared with the volume of the solvent water. Okay, so second of all, how are you going to collect the water at the end? Because right now you've got a precipitate has formed, right? What happens to the water that stays on the filter paper? It evaporates out. So the water you have left is not there anymore. And this amount would be smaller than the amount that would be left on the filter paper. So it's just really not a practical thing to do at all. Yeah. Yeah.
I have a question for the other topics.
Yep.
The solvent.
Yes.
Tend to be like the metal, right? Or
well, usually an ionic compound or a molecular compound. Yeah.
Yeah, and the solvent goes into the solvent.
Yes.
Right? The solvent is like, for example, acid or base, right?
The solvent would be water, usually. Water.
Water.
Yeah.
And what they make is the solution.
Yes. Yes. You can have other solvents other than water. Like let's say you wanted to dissolve something which was nonpolar. You would need a nonpolar solvent because polar solvents don't dissolve nonpolar solvents because they don't mix well due to the difference in intermolecular forces. Yeah? Yeah. For this one, I feel like pH would not be awesome because what happens is over here, you have hydrogen ions and you have hydroxide ions. And reactions where there's kind of a couple reasons. These together make water. pH measures differences in those two concentrations of ions, right? Do I have more H plus or do I have more OH minus? Well, If I put in equal amounts, I would have the same, right? And at the end, they would turn into water, so it would be the same. But the other problem that we run into with a reaction like this is it really takes place very quickly. So measuring a pH, no, we just can't because we have both over there. Yeah, I'm going to just stick with that part of it. We'll talk more about the speed of it later. Yeah. Algo anything else? No? Okay. In that case, we are going to move on to 1.2a. This is on page 29. And this is the rest of what is going to be on your quiz. And we're going to start by watching a little video. Sorry, the intro music is really loud. So I'm just muting for a second here. Okay. Okay, so having seen that, you now know everything there is to know about section 1.2. Okay, we're going to delve into more depth, but if you remember that, you have remembered 5/6 of what this section is about. Okay, so first of all, on page 29, you can see that if we have our reactants and our products, and we could use these pens to simulate those, okay? If they are going to react, and maybe if these guys are going to switch caps, for example, they have to collide this way. Will they be able to switch caps if they collide this way? Will they be able to switch caps if they collide like this? No, they have to collide in a manner where those two caps are right beside one another. So when and if those bonds break, new bonds can reform because the particles are right close by one another. Okay, so first thing we need is a collision. Okay, so the first thing we need is that particles must first collide. For a reaction to occur, particles must first collide. This is what we call the basic premise or the basic idea of collision theory. So that's sort of step one. You got to have a collision. Step two, can't just have any old collision. For a collision to be successful or to result in a reaction, the particles must collide with, and I really want this to be an A and a B, so I'm going to change that to an A and a B. A, the correct geometry. Okay, so orientation is another way of saying geometry. So if we say up here, if we say the wrong geometry, that would be the wrong orientation would be the same as wrong geometry. You could also say the wrong alignment. Any of those words will work, and you will see them all in different contexts. Okay? So, if you have the correct orientation, successful collision. If you don't have the correct orientation, not successful collision. Although I kind of lied there, because even if you have the correct orientation, what if these particles are moving super slowly? Is there enough energy there to break these bonds? No, and if you cannot break the reactant bonds, then you can't form into new bonds, new products. Yes?
The wrong orientation, how do you observe that?
You don't observe it.
Oh, so
Like, you can't see the molecules.
yeah, then is it just like a theory?
It's a theory, yes.
But it's sufficient energy is like proven, right?
Yeah, although, I mean, quite frankly, the orientation thing, I don't know how they've done it, but it's a theory in the sense that gravity's a theory. Do you know what I mean? And that atomic structure is a theory. Theories are basically not like a hypothesis, not like maybe we're right, maybe we're wrong. It's like there's a whole body of evidence that supports this, and it explains a whole bunch of things. And so we have observed nothing in a whole bunch of observations and data that contradicts this theory.
Yeah.
Okay? So it's not theoretical in the sense that it's like, oh, it might be, it might not be. We know it. I mean, you can't see the force of gravity, but you can observe its effects.
Yeah.
Right? I think it's like that.
Okay.
Just go with it. Okay? At least for this course, that's all that matters.
Yeah.
Okay? Talk to your university professor about those more in-depth things, because I'm like, I don't know. Maybe someone did observe something at some point. I don't know. Yeah? Okay. So in order for the collision to be successful, we have to have the correct geometry and we need to have sufficient energy. Is there another word that you guys know for sufficient? Enough. I.e., do you guys remember what I.e. means? In other words. It's from the Latin id, est, that is, as in that is to say. So i.e. means, in other words, enough energy. Another word for a successful collision is an effective collision. So you need to be familiar with both of those terms. Okay, so a successful collision is also known as an effective collision. And while we're here, I might also mention never say enough sufficient energy. I don't usually get this with my AP class, but every year I get someone in my class who uses the term enough sufficient energy, as though sufficient energy were a type of energy, like kinetic energy or something like that. This is like saying enough energy. Okay, so don't do that. And according to collision theory, the greater the frequency of collisions, how often things collide in a given time, the faster the rate. So more collisions in a given time, faster rate. And remember, they needed to collide with enough energy for the books to scatter. There needed to be enough energy to break the bonds. Okay? So the greater the energy, the more likely you're going to have that. Every bond has a different amount of energy, so there's going to be a minimum energy needed to break those bonds. Okay? So the greater the energy of collisions, the faster the rate. Now, when we say energy of collisions, are we talking potential energy or kinetic energy? Things collide with kinetic energy, okay? How do we measure kinetic energy of particles?
Heat.
Not heat, but you're on the right track. Temperature, yes. Was that what you were going to say too? Stole his thunder. It's all good. Okay, so we would measure this with temperature. So if you have a greater temperature, the collisions will have more energy, and therefore you'll have a faster rate. Okay? Temperature measures average kinetic energy. So higher temperature goes to more higher energy collisions. And I don't like creating the word collisions a lot because we write it over and over. So I just write COLL with a little NS up at the top, and that stands for collisions. These guys here, I should really put this in a box because it deserves a box, right? Because it's a little summary. There are 6 factors that affect the rate of reactions. 5 of them can speed up or slow down a particular reaction. The first 5 speed up or slow down a particular reaction. So that would be your concentration. If you change the concentration of a reactant, you can speed up a reaction. If you change the pressure or volume, as long as you've got gases, you can change the speed of the reaction. If you change the temperature, you can change the speed of a reaction. Change the surface area. As long as you have a surface, which is what we mean when we say heterogeneous reactions. Those are reactions in which there is a surface between this thing and that thing. We'll talk more about that later. If you add a catalyst, you can speed up or slow down a reaction. Nature of the reactants does not speed up or slow down a particular reaction, but it does explain why some reactions are faster than other similar reactions. So this last one, explains why reaction A is faster than reaction B. So that one's kind of different. So if I say, how could you speed up this reaction? You could say I could increase concentration, I could increase temperature, I could increase surface area, I could add a catalyst, I could increase the pressure, but you couldn't say, I could change the nature of the reactants because now you're looking at a different reaction, right? All right. Yeah.
Increasing the surface area.
Yes.
The solvent, the solvent, right?
It's a little more complicated than that. Anything that has a surface. So if you had a liquid, say in a container that's about this size, 3-inch diameter or whatever, and you put in, your 50 milliliters, it would have a certain amount of surface. And if something in that liquid were reacting with a gas, we would have a certain surface. But if we then put it in a 3-foot wide diameter circle, it would be this huge layer spread out very thin. You would have a bigger surface. Okay, but mostly it has to do with when you have a solid with something else, because a solid always has a surface. Okay, so 95% of the time when we're talking about surface area, we will be talking about a solid with something else. It could even be with another solid. Okay, but this one usually a solid. Powders are solids. Yeah. So if you had, let's say you had a piece of chalk, okay? Have you guys ever seen a piece of chalk? Okay, you still use them even though we don't have chalkboards. Writing on the road and stuff, right? Yeah, okay. Anywho, if you have a piece of chalk, you could put it with some acid and it will react with the acid. If you crush it up, it will react with the acid faster. Yeah? All right, so let's look at each of these in a little more detail. And remember, we are looking for things that increase the frequency or things that increase the kinetic energy or both. So for reactant concentration, here's an aqueous concentration. If we have more particles, in the same space, what would we get? That makes it so there's more reactions, more collisions. And to be more specific about that, we will say an increase in the frequency of collisions, because then you don't have to say more collisions in a given period of time. Yeah, because that becomes wordy. And you can just say that by saying we increase the frequency of the collisions. Now remember, successful collisions, the percent of collisions which are successful, that's going to depend on whether the collisions have what? Enough energy. And what changes the amount of energy? Temperature, right? If we increase concentration, have we increased the temperature? No, right? If I have, a drink mix and like I, put a little bit in some water and I stir it around, it is at the same temperature than if I put a whole bunch in and I stir it around. It's still just at room temperature, as long as my water's at room temperature, right? So there's no change in temperature. No change in temperature. Therefore, the percent of collisions with enough energy stays the same. So we've gone from having, let's say we had at a low concentration, let's say we had 10 collisions per second, okay? And let's say 40% of those have enough energy. So 40% are successful. So 10 collisions, 40% have enough energy. So how many successful collisions would we get? 10 collisions per second, 40% have enough energy to react. How many collisions would be successful per second? 4. Now, what if we had a high concentration? Now we're going to have more collisions. We're going to make our numbers really easy here. We're going to say, oh, let's have 100 collisions per second. We have not changed the temperature. What percent of those collisions would have enough energy? 40. Still 40%. And so therefore, how many successful collisions would we get per second? Oops. 40 successful collisions per second. Is that all kind of making sense? Concentration is usually not that difficult to visualize, so it's kind of the nice one. It's like, yeah, more collisions. Nope, no more energy. Okay, so it only increases the frequency of collisions. It does not increase the percentage of collisions which are successful. All right. Next, we are going to move on to pressure/volume. And this is where you change the pressure by changing the volume. There are other ways of changing pressure. You can change pressure by changing the temperature. We're not going to do that because it just gets too complex. Now you're dealing with temperature and pressure and you're like, ah! So we're going to deal with temperature just as temperature. Okay. You can change pressure by adding another gas to the mixture, which we will look at later. Okay, but not yet. Right now we're just looking at, we are making pressure go up. If I want pressure to go up, do I make my container bigger or smaller? If I want my pressure to be bigger, smaller, because now I've got the same amount of particles in a smaller amount of space. They're going to bash into the container walls more frequently. Yeah. And they will also bash into each other more frequently. So you're going to have an increase in the frequency of collisions. Have we changed the temperature? No change in temperature. Now, technically, if you change the volume of a gas, you will probably also have a temperature change, but we're just going to assume that we're only changing that one variable, okay? Because if we start having temperature and volume and pressure, like I said, it gets too complicated, okay? So we assume there is no change in temperature. And if there's no change in temperature, will there be a change in the percentage of collisions which are successful? Nope. Therefore, no change in the percent of collisions which are successful. I don't know why I write this. It's written right there, but that's okay. Okay? No change in the percent of successful collisions. So basically, if you want to speed up the reaction, you make the volume smaller and the pressure bigger. If you want to make that reaction slow down, you make the volume bigger and the pressure smaller. Okay, remember, as P goes up, as V goes up, P goes down. As V goes down, P goes up. Okay, but hopefully you guys know that by this point. Or it's kind of intuitive. I think it's kind of intuitive. But anyway. All right. This is just another picture. I don't know. I like to see it. I don't know. I found these pictures. I was like, I can't leave it out. It's just so nice. Okay, now we have another way of changing the pressure. Not this one. Here we go. Yeah. Okay, so if you increase pressure by decreasing volume, the rate increases. However, if you increase the pressure by adding an inert gas, what the heck is an inert gas? What does it mean if something is inert? It does not react, it's unreactive. If a gas is unreactive, what kind of gas is it probably? Probably a noble gas. So if I have these are my reactant particles. Okay, and this black one, those are my inert gas. There should be stoppers on these things. When we add the inert gas, what has happened to the pressure? It goes up. Overall pressure increases. What happens to the number of collisions between reactant particles? Stays the same. BW means between. Sometimes people don't like that they stay the same. There's more stuff, there will be more collisions. There will be more collisions between any old particles, but you're going to have more collisions between reactant particles and non-reactive particles, but the ones between the reactants themselves will stay the same. The other thing you have to remember is, of course, that how much volume do the actual gas particles take up? We're going to assume that they take up no space at all. Okay, and if you imagine these particles taking up no space, then the inert gas won't, they just don't affect the collisions at all. Okay? So there's no change in the rate. Temperature is the fun one. Okay, because up until now, we've been like, concentration, do I get any extra energy? No. If I change the pressure, do I get any extra energy? No. Temperature, do I get any extra energy? Yes. Okay, because when I increase the temperature, that is the same as an increase in kinetic energy, which leads to an increase in the percent of successful collisions. However, you also just get an increase in the number of collisions, right? If I cleared out all the furniture from these rooms, got rid of all the desks, all the lab stations, all of that stuff, and I blindfolded you all and told you, walk around the room slowly, just go for a stroll, okay? Would you collide with each other as frequently as you would if I said, okay, everybody, now you run around the classroom? Where would you get more collisions? Running around the classroom, okay? And also those collisions would have more energy. So you get both an increase in the frequency of collisions and an increase in the percent of collisions with enough energy to react. So, increase in frequency of collisions, increase in percent of successful collisions which are successful. I don't know why I wrote that, because it says it right there. That's okay. Okay. Next, surface area. Surface area is for heterogeneous reactions only. Most often, you have at least one solid, okay? Now, I'm going to use the word phase here. Phase has a special meaning in chemistry. And sadly, up until this point, you've probably heard the word phase and you think state. Am I correct? Okay. It's solid, it's liquid, it's gas, that's its phase. It's a little bit different, okay? A phase is a certain area of the universe that has all the same properties. In other words, if it has all the same properties, it is homogeneous. Yes? So if you have one phase, you've got one area of the universe that has all the same properties. That is homogeneous. You might have a block of aluminum. Yeah? It's all the same. Aluminum always has the same density. It's always silver. It's got the same melting point, right? There's nothing different in any piece of that aluminum, okay? But I could have two phases. I could have a piece of copper and a piece of aluminum. Those are both solids, the solid state and the solid state. Are those one phase? No, because remember, they would have to have the same properties. They don't have the same conductivity. They don't have the same color. They don't have the same melting point. Those properties are different. So you can have two solid phases. Okay, they're just made of different stuff. Okay. So actually, I'm just going to skip over this part for just a moment and just go down here. If something is heterogeneous, that means that we have two or more phases. A homogeneous reaction has only one phase. However, I brought this up because it is important for you to know what a phase is. But you can also just think, if I had this and that, would there be a surface between them? If I gave you two gases as reactants, would there be a surface between the two gases? Or do they mix? They mix. Yes? You can't increase the surface area of a gas and another gas in relation to each other. If I had a couple of aqueous ions and I poured them in there, can I increase the surface area between the ion A and ion B? No, there's no surface between them. They're all in the water. Yeah? If I had some acid and I threw in a chunk of solid zinc, is there a surface between the acid and the zinc? Yeah, right? You've got, this has a surface, right? So don't get too wound up about the whole phase thing. I mean, it, like I said, it's important for you to know the word because at some point, it makes you more literate. But just think about it. If it's heterogeneous, I've got two things that have a surface between them. If I don't, then I don't. And usually to have a surface, you need a solid. But you can have a surface if you have solid A and solid B. So for example, I think if you have, is it barium nitrate and ammonium chloride? Whoops. I think so. I could be wrong. But that's an example of actually two solids that you can mix together and you will get a reaction. Okay? And there is a surface between them. If you had one chunk of each, let's make this one like this. Let's make this one like this. Yeah? If I put them together and I have a chunk of A and I have a chunk of B, we have a surface between them. But if I crush up A and I crush up B, what's happened to the surface between them? There's a whole lot more surface. Yeah? I think it's fairly straightforward to know that if you have a solid and a liquid, you are going to get a surface. That seems fairly reasonable, yes? Okay. If you have a solid and a gas, is it self-evident that you have a surface? Yes. Solid and aqueous, you got a surface. I think the solids are really easy. If you have a liquid and a gas, you can have a bigger surface or a smaller surface. Same thing with aqueous and gas, because the aqueous could also be in that liquid. Okay. You could even have two liquids, oil and water, for example. I mean, the two of those don't react, but you could find something where you have one liquid A and liquid B. Yeah? Liquid A and liquid B, and you have a surface between them. This is phase one, phase A. This is phase B. If those were oil and water, they have different properties in those different areas. So those are heterogeneous because there are different areas with different properties. Homogeneous, can you separate, if your liquid is water, can you separate that from your aqueous ions? Are they separate or are they all mixed together homogeneously? They're all mixed homogeneously. Aqueous and aqueous, all mixed homogeneously. Gas and gas, no surface. If you have two liquids which are miscible, are you guys familiar with the word miscible? Miscible means mixable. Okay, immiscible means unmixable. And you should know those words. And we're going to skip ahead because we should get through a catalyst. All right? So, catalyst. It speeds up a reaction by lowering the amount of energy required. So you can think of this like a high jump competition, okay? If we have a higher bar, a smaller percent of athletes can complete the jump, can successfully get over. If you have a lower bar, a larger percent of athletes can successfully get over the bar. What a catalyst does is it lowers the bar. In order for these two to react, we need enough energy to break the bonds. And the bonds have a certain amount of energy, yes? What a catalyst does is it somehow or other weakens those bonds. Okay, so it makes it easier, or it provides an alternate pathway with smaller energy needs. We'll talk more about that later. Okay, but basically, just from an analogy standpoint at this point, you can see we have down here, this is a potential energy diagram. Do you remember we had our reactants and then our products? This particular reaction would be exothermic, right? Reactants, products. In order to break the bonds, here we are breaking the bonds. Up here, the bonds are broken. And then as it goes down, new bonds form. If you have a catalyst, there's a lower peak to get over. So more collisions will have a higher percent of collisions will have that amount of energy. Does that kind of make sense? Okay, we'll talk more about that later. This amount of energy that's required to break those bonds is called the activation energy, and we'll look more in depth at that later, but that's where we're going to get to for now. You guys are going to read and watch the videos, pages 35 to 37, and do the questions on page 37 to 40. That is on our teams. So no worries. You can go up there and take a picture of that, or you can look on Teams or whatever. Okay? 35 to 40. Read, watch, and do. Next class starts at 1:53. So it's like a half an hour flex.
Yeah, no. Yeah. Wait, so. Yeah. Oh.
Yes.
So activation energy is the minimum amount of energy needed for collision to be for collision this.
This is whipping up.
Yeah. But this one is right. So. So for the collision to be successful, we need to take first micron.
Hi.
Like I have a question about this.
Yes.
Like the answer said the small amount of water it's insignificantly, but
Mhm.
what about big amount of water that can be
I
acceptable?
know. If you've got water as a solvent, any water that's produced in a reaction is going to be minimal compared with the amount of solvent.
Oh,
Yeah, so if you have
so-
anything where it's aqueous and then you're producing water,
yeah.
if you had a reaction where it was like, say you had H2 gas and O2 gas and you made H2O,
Yeah.
then it's okay because there's no solvent,
Oh, I see.
right? You don't have any water just kicking about.
Oh, like this one?
Uh-huh.
The pressure is increased.
Yep.
But why is that the reaction rate stay the same instead of decrease? Just
So
like
for every particle, like let's say that this one, instead of say this one was moving this way and it could end up colliding with that one. Oh no, it's blocked, but it bounces off this one and then it collides with that one. So for every collision that is blocked,
Yeah.
another one will
Oh,
occur, right? It just that statistically it works out so that you'll end up with the same amount of reactant particles colliding.
Okay, thank you.
Yeah, cool.
Okay, so an enzyme, for example, often is yeah, so that's one type of catalyst. Well, let's say we have reaction A. So now we have like carbon C called reaction C, we'll get to that later. And then this is it, right? This reacts with the of and then the end. Right? And it's no energy barrier for small. probably this is fine.
Yeah.
Or I might say, you know, if you said yeah, measure a change in color using. I'll be back in like 1 minute. I just have to pee.
Roughly just for any like, oh, this is radical, or irrational. Maybe like.
Well, experience before.
What?
Oh, wait, cool.
You're on the square root, that's recording. Square root is not bad.
Bro, because you can't represent the answer, so is it radical as a radical? Yeah, that's right. So it's still one. Bro, you don't know what's square root. Yeah, it's not.
What kind of stuff is it?
It can't
No,
go
it's not. Is it radical or beyond?
Yeah. But just terminating like one of your direction as.
Well, terminating is like so to Brian Elfin. It's irrational.
It doesn't, it's not repeating, it's not.
You can't be right at 5 that's rational. It's at 1.41. Oh yeah, don't estimate like it wasn't it not a person whatever. One person say how you estimate it.
Right.
Closest.
I is square.
But there's no perfect square.
Yeah.
Or a square root of even.
Well, like, if you're you try to use that, what's this represent that one with if you could
So you
represent
got perfect squares and there's one. What's the next one? 3.714.
Right, then I just, so it's important. I was on the, a bunch of people on Euler. Some people who got a 5 8 about repeats, Euler. Oh.
Yeah.
If it is.
So there we go, we got this
Well,
one.
it's not
So our, yeah.
Bro, I'm learning right now, so because it's hard and it's absolutely
Okay.
integration sucks.
Well,
It's right. If it's an
sure. Yes.
One over x squared plus one.
We're not wondering, is it 10.1? Or is it at 9.9? We're not wondering about that.
I can go back to the.
Yeah, so it's a 10.0. Yes. Yeah. And then the number is one.
You can say all that extra.
Wait, so you can just, I thought it was like. Oh my god. I thought it was like, well, one over x.
Yeah. Yeah. So there's rules of zeros.
Let me grab a pen here or pencil.
Oh, man.
No, it actually do it whole formula, but that has the numerator has to be solved for one of the derivative of this and the numerator should have x. X to the power 1.
Because
If you think about it,
Bro, I forgot hold on.
zeros are left.
no, you're not.
No, you remember yourself.
Yeah. Always. Zeros at the end. It's Yeah, so like if
I don't
you
think
have,
this that's
so this one is, if you have exactly in the number anywhere.
You really do, it means scribes in its financial.
No, so if I
It
have
means
7,000,
scribes.
that's one. Yeah, just say that. But if I say you have 7,000 decimal hundred, now I'm, if I have 7,000, 0.5. Okay, yeah.
Alright, I'll.
Okay. So did you want this one? Yeah. Okay, cool.
So basically, sign up for industry courses on So this first two blocks are outside, this next two blocks are outside. It's like an hour trying to see. So.
Did you want the regular or the enriched version?
Okay,
perfect.
And this.
I just gave you one, that's good. Right?
What if
You're late.
You can say it's an area of space where water is the same.
Oh, so it's an area of the universe we're all talking about.
Yeah.
Hold on, it's asking about the volume.
This one is not really great to do that with because you have both hydrogen and hydroxide. So this is technically neutral and so is that.
Oh,
Yeah,
and then the ones there's
I would say don't use the pH reader.
Wait, but if you have
Not for
pH meters for all the acids, acids are like.
Well, it's just for aqueous hydrogen peroxide.
So if there's only either hydrogen or peroxide.
Yeah, yeah,
But otherwise.
not for measuring rates.
Yeah.
Now, if you were doing a titration between these two, if you were reacting them and not worrying about how fast it went, you would start with maybe say acid, the pH would be low, and you could say, if you're plotting it instead of versus times versus volume added, and then you could use a pH meter to see how the pH changes with volume added, but you're not doing it as a rate.
So if it's
at that point.
neutralization.
So then what would you use for this?
For that one, I would probably find out where you've got lots of ions, is where you have more ions. You could theoretically do the mass of the solid roots.
So you can do mass of this or conductivity of this. Or this.
Well, not conductivity of this or this, because you can't separate them out, they're all in
Right, because they're in
one.
one.
Yeah, so you do conductivity of this or one.
Yeah, so then when the reaction increases, like the conductivity goes to the
Yeah. Correct.
Oh, so this is ion, right?
Yeah.
So it's OH.
Yeah.
And then here, ion, but.
But they're not dissolved, so they don't conduct.
These are also, these ions?
No, they bond covalently.
Oh, I see.
Yeah.
Thank you.
Yeah. Mm.
Nobody else said.
Okay, so for here, what we've got is we're going to start over here. So we have electron clouds.
I don't think I explained from any of them.
Around the outside, some of them negative electrons. So but in the middle, we have nuclei. I don't know why I'm drawing a nice picture, okay, because I've made a mess of it. Anyway, so the nucleus sees the electrons in the other one, and these attract.
Oh, yeah.
And that's the dominant force at this point. That is the force that is stronger. But instead the repulsive between the two, the electrons and the electrons.
Should I consider like potential energy?
Yeah, because as they get closer together, they're going towards the state. It's like when this gets closer to the Earth, it's going to stay closer. So as the negatives get closer to the positive, that boosts the state. Yeah?
Yeah.
And that's why as you can see the potential energy decreases. Now, at some point, these two nuclei start to get too close to one another and they're like, we're going to repel now. And so that's why the potential energy starts to increase again. So if you had, say, a string, right, and it's just in its neutral state, you could pull the ends apart, right? And it would be like, it would want to go back here. But if you kept pushing it, then its potential energy would be higher. Right, so you start with a high, and then it's at its low state, where it stays, if you don't put any force on it, and then you can switch it so that it's not going to go back up.
Like because you want to know each other, right? But why is that the distance? It's still decrease.
Yeah, I mean, you can, if they smack into each other with a force, they'll get closer to each other, but then it'll like.
Oh, I see. But that process is not speed.
No, we just show this process. Right?
I see.
But really what you get is you get.
And those two are all like propel and traction extension.
Yeah.
Thank you.
Yeah, no worries. This is very good. Okay. I'm sorry, there's no comments.
That's like it's just.
Yeah, for sure. Did you have a regular? Regular?
Like everything strong. Oh, but what if we like like on police like that or the private world? It's badly done. You don't have usually has to be like not like if you use like all these other roots, it doesn't care. It has to be like masterfully like this. You need like like you need all the right evidence. Like if you miss something, that's just gonna go down. I got 90. I'm getting higher because recently I was so that was recently.
And I figured it was fine. I'm just yeah. For you guys on software, I mean, oh, but then like
I know, like, so sad.
we did anyway. That's just fun. I just want to say
Yeah.
and I got on.
This one, we have the right here. First one, this one.
So I added.
All the things.
Yeah.
I guess it is. Position I got.
Yeah.
I'm pretty sure I got a bag of comments.
I think they usually did.
Sometimes.
Sometimes they run out of water.
volunteering or something like that.
Everybody was lying,
I feel like it's just too much. It's like. And it's like, people like, what's your activity? What's your, it's like, a lot. What else? I can maybe ask you something. So as for She's volunteering. So that's, you don't need to do that. Oh yeah, that's. Literally all you do is like drink this to that and then take home. Someone. We got to get all you have to do is act like you're not jolly. You're actually not jolly. You're like, jolly, like a serial killer. Right. Or you're like, right, I'm like certain tickets are actually like breaking sign. Hey, I'm like, this guy was reading like, I'm gonna go on this private. So that. I don't think it's small is very well. Yeah, there's like one you. Yeah, it's one that you. Yeah.
Yes, it's 1 cent, right? You're not unsure about that.
There's a note in it. It's really more actually was made there. Rather than this, against you. It was counting. I counted on school. So there are the lines are pretty sure I'll be awesome. This is just I can show you. Wait, what about 0.1,000? Oh, it's overall. Three, like, yeah. You are not. Did it? I was gonna finish it. Quick word, get out.
Yeah.
Which of the first four factors of nature react?
And then
Those are 5 minutes.
That's what I mean.
Yes.
Okay.
I didn't know what to do. So
Yeah. You just took a few notes?
No, these were the notes.
Oh, okay,
before,
okay.
but
Yeah.
I just wrote these down
Yep.
because I didn't know what we were supposed to do. So I did them. Like
Okay.
I did the
And you guessed what the sig figs were? We're gonna go over it today as well.
No,
And
I actually,
okay.
like I didn't know what we were supposed to do with the video, so I just took down notes from the
that's
video.
good. That's all you needed to do. You can. I'm just gonna record these ones real quick because I got a couple people who just wrote it and then I'll get it back to you, okay? So yeah, it'll just be a minute.
Last year's, I was yeah, like, I'm saying study, like, I didn't have time. So I was like, okay, I'm sure after this sort of, I'm not gonna have it. I was not gonna miss you. I was just like, yeah. This one, I was lost in that.
Jennifer.
Yes.
There you go. I'll just hold on to that. Yeah. Yeah. Yep. You can keep that. Okay. Or you can recycle it if you don't want it.
I didn't turn it in, but I finished it.
Okay, could I get it from you? Sorry.
Okay, let's see if it's something.
Okay, and if you don't, I can get you the video real quick. That's okay.
So you didn't like. Dark.
Better know what
Yeah, I know.
Anyway, if we find it, that's great, if not. Okay. Sort of being the strongest.
Spicy, someone's getting.
I didn't know that. Oh, no, wait,
No.
They're the same. Oh my god.
Okay. So here I have got.
Huh? OC War? Yes. I'm here for that. I love how you
Thank you. Perfect. Thank you.
I swear my S was supposed to be a large letter.
Okay, I just found these back now. Oh, yeah.
I can see you. Probably or do you see it on your bed? Take on.
Amaya.
Oh, I didn't use that. Oh, he found my app. Oh my god, is this powders? Oh, here.
This is, no, this.
Wait, that's.
I feel like she's still.
Like, oh.
Are they?
And at least now this and her I would go.
I think that's a little.
It's not. I don't want to like actually like you go.
I did, yeah. After the Lord.
Okay, my friends. Is there anybody who did not get their quiz back yet? Everybody got their quiz back? Has everybody remembered to put their phone in the cell hotel? Okay. If you've not remembered, go do that. And your homework last day, let's get rid of this because this is just going to confuse you. This is my grade 12s. Was pages 28 to 32, numbers 3 to 7, and 10 to 13. So if you want to come up and show me that, you may do so. Alrighty. Excellent. Excellent. Good. Very nice. Thank you very much. Good. Hello, Valerie. Thank you. Thank you. Very nice. Awesome. Thank you very much, Valerie. Valerie. There she is. And hello. Excellent. Oops. There we go. Very nice. Thank you, Abby. Hello. Excellent. Perfect. Thank you very much, Matthew. Hello. Excellent. Let's keep going. Excellent. Awesome. Thank you so much, Sophia. Way at the bottom. There we go. Hello. Excellent. Thank you very much. And thank you, Malia. There we go. Hi, Sue. Excellent. Very nice. Very, very nice. Awesome. Perfect. Thank you. Hello, Cody. Awesome. Yeah. Very nice. There's a few where you don't have your units, so just watch out for that. Okay, so check for your unit there. Great. Hello.
I did everything except
Yep.
for the last two questions
Okay.
because I couldn't understand.
That's
them.
okay. We'll go over them today, so no worries about that. You're perfect. Okay? Yeah.
No.
Hello. Excellent. Very nice. Nice. Thank you so much, Sarah. Hi, Ken.
That's fair. I should put that on my
Awesome.
Some of my drawings from Chinese people.
Units. And other than that, looks good. Okay. And hello. Very nice. Yeah. And just watch out to have your units in there. I know you had them before. Wonderful. Thank you very much. Hi, Spencer.
Hi.
Awesome. Nice and nice. Thank you.
The fact that you have put in.
Hello.
I love that style.
Yeah, there we go. Excellent. Very nice. Awesome. Thank you so much.
I love that, like.
Hi, Mateo. Do you guys mind sitting up here? I think they just co-opted your spot. You're okay? Okay, good. Awesome. Thank you very much. And I just want you to watch out for putting your units at the end of everything.
Oh, yourself?
Yeah?
Changed so much.
All right, Mateo. G. No? D. D. There we go. Hi. I had a freak out for a second, but it's Amaya. Yes. Okay. Sometimes when I've gotten something wrong enough times, like my brain starts to go, I just don't know, but I know now. Thank you, Amaya.
Thank you.
Hello. Emily.
Yes.
It's so funny because your last name starts with R-O.
Yeah.
Like, I keep thinking your name is Robin for some reason, and I'm like, but it's not. Emily. Okay, very good. Very
And then
good.
Rodney, yeah.
Rodney, yes, very
I was
nice.
talking about Allison, so that's my mom's name, so I was like,
Oh, that's nice. Very good. Okay. At the very river at the very bottom. That's right, because I added you on. Thank you. Thank you. Hi, Smiley. Fantastic. Thank you, and thank you very much. Hello. Awesome. Thank you. Those are looking good. Thank you. So, hello, Kira. Excellent. Wonderful. Excellent. Very nice. Thank you. Austin. Hi. Vivian. Awesome. You did. Yes, you did.
all right then.
Vivian Robinson. There we go. Hello, Aria. Very nice. Don't forget your units. Okay. And yeah, that's a capital N. Okay. Yeah. No, that's not a capital N. Lowercase f?
Yeah, but
Capital N. Hi. I gotta write down Aria before I forget. Jennifer. Excellent. Perfect. Thank you. Hey, there we go. And you weren't here, so did you manage it? You tried?
Yeah, I
Yeah, okay, that's good. That's good. We're gonna go over some of them today, so hopefully that'll help you out if you had any difficulties. But it looks like you're good. Because that's the correct answer. So yeah. Oh yeah, I gotta check that one too.
Yeah.
Perfect. And then just one more perfect. Thank you so much. Zoe, there we are. Perfect, thank you. All right, who am I missing? Just Max, did you show me your work? You did it yesterday. That's right. Why did I not write it down? Because I'm an idiot. Okay. Ryan, do you have your homework? You're okay right now? Okay. Show me later, okay? Okie dokie. Paul.
Actually,
I noticed when I was checking everybody's work that many people got the same question wrong. I didn't mention it to you when you were up here, but we're going to go through those ones that were tricky together, okay? And if you got them right, you can be like, "Whew, I'm so smart." Give yourself a pat on the back and be like, "I'm a genius." But it's okay. Most people get them wrong the first time through. My grade 11s, if you get me for grade 11 chemistry, you'll actually do this exact same thing. But you won't remember it, so it'll be okay. You might remember the principle, but you won't remember the exact numbers. All right. So we have here, come on, there we go. All right. It was on page 29. So if you could turn to page 29, Number 4. And I need to, oh, I'm still recording.